Hello everyone, my name is Viraj, and today we'll be looking at the 23rd problem from the CP-31 sheet by TLE Eliminators under the 1000 rated questions. Let's go. So moved on to my sheet over here, ticked off 1000 and 23rd problem, different divisors. Okay. Positive integer x is called a divisor of positive integer y if y is divisible by x without any remainder. For example, 1 is a divisor of 7, very obvious. 3 is not a divisor of 8. You have been given a single integer d and you are asked to find the smallest positive integer a such that a has at least 4 divisors and difference between any two divisors of a is at least d. Okay, very simple problem. Let us quickly generalize this. They are saying that they will give you a single integer d. Okay, what do you want to print? You want to print a number a. This number a is the smallest positive integer such that it satisfies two conditions. The condition number 1 is a should have greater than equal to 4 divisors, or you can say factors, whatever name you call it. It should have at least 4 divisors, that is greater than equal to 4 divisors. Second condition is, if let's say that these divisors, I'll just name them. Let's say the divisors are d1, d2, d3, d4, d5, so on, so on, so on. Let's say they have at least 4 divisors of a. If I pick up any two divisors, any two, let's say I pick up random d2, let's say I pick up d5, any two divisors, their absolute difference should be greater than equal to d. More so, you can say that from this set, if I pick up any di and dj, then absolute difference, you can say something like this, absolute difference between di and dj should be greater than equal to d. This is where this d integer comes into picture. So you have to print such an a which is the smallest positive integer and satisfies these two conditions. So a should be smallest positive integer. Okay, let's take an example and I think stuff is going to be much more clearer. For example, d is given 2 to us. You can check the sample cases and a in this case turns out as 15. Why? Let's first print the divisors of 15. 1, 3, 5 and 15. You have at least 4 divisors. To be specific, you have exactly 4 divisors in this case. And you pick up any two. I'll give you 2 minutes. Pick up any two. Pick up 1, 5. Pick up 3, 15. Any two. You will find that their absolute difference is greater than equal to 2. That means a is correct. And arguably 15 is the smallest positive integer which satisfies for d equals to 2. Hence this is the answer. Now added to that, let me give you one more answer. If I feel that d was given 3, answer according to me, okay, answer according to me, a should be actually 55. Let's check. Print the divisors of 55. 1, 5, 11 and 55. At least 4 divisors. Again, exactly 4 divisors in this case. So that is at least 4. Satisfies. And pick up any two. Pick up any two divisors. 1 and 5. Or maybe 11, 55. Or maybe 5 and 55. At least difference 3 is there. That means 55 is right. And this is arguably the lowest positive integer, which is correct. I hope the cases are clear. So first of all, we need the time complexity. We have time limit per test as 1 second. So that means that one test basically tells me 10 raised to 8 operations. Now I have been told that in one test, there are some test cases that is by 3000 of total size. So if I want to print the number of operations for every test case, then I can write this as 10 power 8 upon 3000. That is something like 1 by 3 into 10 raised to 5. Now 1 by 3 can be something like 0.333 something. So you can write this as 3 into 10 raised to 4. It's like a rough approximation. That means in order of 10 raised to 4 is what is allowed for every test case. Now if I look for d actually in the problem, d is 1000. Let's look at d. D is given in 10 raised to 4 order. So you can create a solution that runs in O of d complexity. You can even create a solution that is anywhere lower than this and maybe up till constant time. But as soon as you cross O of d boundary, I think you are going to exceed and that is going to create a time limit, exceed it for you. So that means solutions like this are promoted and anything above this is not allowed. And this is my expected time complexity, which is again very helpful because now this is telling me that if you go for every test case based solution, don't cross an O of d boundary. Okay. Expected time complexity. All right, helps. let us begin with the idea. Now, first of all, there has to be a very important idea that is going to get propagated in our later ideas. Idea number one. We are trying to create at least 4 divisors for the number. Now, at least 4 divisors means 4, 5, 6, even 10, 100, everything satisfies. But tell me, let's say there is a number capital A. It has, let's say, 10 divisors. There's a number capital B. It has, let's say, 4 divisors. Now, both of them have at least 4 divisors. But which is bigger? The number which has 10 divisors, will that be bigger? Or the number which has 4 divisors, will that be bigger? Of course, the number which has 10 divisors is going to be bigger, because more divisors, that means the number is even larger. So it has more factors that are coming into that number. So do you think I would want to prefer the number A, or I would try to find a number that looks like A? Go for 10 divisors. No, right? Even B equals to 4 satisfies, as in not B equals to 4. B equals to 4 means even a number which has exactly 4 divisors also works for me, right? So I want the smallest positive number. If I want that smallest condition to be greedily satisfied, I will not work with at least 4 divisors. Rather, if I actually work with exactly 4 divisors, I'll still be good to go. And this is my idea number one. That is, instead of working with greater than equal to 4 divisors, no, I'm actually going to work with equal to 4 divisors. So from now on, my target is to work with the numbers which have exactly 4 divisors. I hope this idea is clear. Now, this idea actually translates to the next ideas. How so? Because now that I have understood I'm looking for numbers which are exactly having 4 divisors, I would, by common sense, now would want to figure out which numbers actually look like so that they have 4 divisors. Let's see. The question is, we want to figure out how many number of divisors does a number generally have? And that is given by a very neat formula. If you have, let's say, a number n, this number n, if it's composite means it is divisible by some other number besides 1 and itself, basically not prime, then n can be represented as the product of prime numbers raised to their individual powers in a general format. N can be written something like p1 power, let's say, alpha. P1 is a prime, alpha is the power of that. For example, 2 power 3, 2 power 5, 2 is a prime and then power of that. Into maybe some other prime, P2 power beta. Into, let's say, some P3 prime power gamma. Into, let's say, some P4 prime power delta, and so on, so on, so on. If I want to figure out how many number of divisors does this n have, the formula says alpha plus 1 into beta plus 1 into gamma plus 1 into delta plus 1, and so on. If you have more primes and they have more powers, plus 1 plus 1 plus 1, so on. And this is exactly the formula of number of divisors of a number n. Let's first take an example. Let's say that n is 12. First, let's represent 12 as prime to the powers. So 12 can be written as 2 power 2 into 3 power 1. Is this correct? 2 power 2 is 4, 4 into 3 power 1, that is 3, that is 12. In this case, now you have nothing more after this. So this is all that can be represented. So you can say this is P1, this is P2, this is alpha, this is beta. Let's see. Alpha plus 1 into beta plus 1, and then I don't have any gamma or anything, so that is all. That means alpha is 2, so that means 2 plus 1, that is 3, into beta is 1, 1 plus 1, that is 2, that is 6. So my argument is 12 has 6 divisors. Let's actually check. Print the divisors of 12. 1, 2, 4, 6, and 12. Voila, you have 6 divisors. So does this make sense? Is this checking out? You can pause the video. You can check this for all other ends. This actually works out. This is like a very elementary formula. Okay, so I've given you an example. Now let's try to do a little bit of intuition proving also. Why is this formula working? Basically, this formula comes from combinatorics. What happens over here is, if we want to represent some divisor of n, let's say I'll call that divisor capital D, some divisor of n can be represented by creating P1, P2, P3, P4, and so on, so on, so on. That is there. And the power that I choose can be anything that ranges from 0 to that original prime's power. That means if let's say I want to ask P1 power, then this power can be 0, it can be 1, it can be 2, it can be 3, and so on till alpha. I have 0 to alpha, that is alpha plus 1 options that I can put for P1. Similarly, I have 0 to beta options I can put for P2. I have 0 to gamma options I can put for P3 and so forth and so on. So these options that I have for individually every prime get multiplied together, and that generates me all the divisors that n can have. That is why the formula states that alpha plus 1 goes for options for P1, beta plus 1 goes for options for P2, gamma plus 1 is options for P3, and delta plus 1 is for P4, and so on, so on. If you have P5, P6, and whatever primes that come in the number, once you actually break them down into prime numbers. I hope this is clear. This is the elementary formula. Now let's use this. Let's come back. Our target is to find 4 divisors. That means this equation that I have just created for myself, alpha plus 1, beta plus 1, you can say gamma plus 1, delta plus 1, and so on. This should be equal to 4. This is what I'm trying to solve. Now, according to me, this has only 2 solutions. Tell me if they are wrong. One solution is you directly keep 4 as it is. If you keep 4 as it is, I substitute 4 with alpha plus 1, and 4 can be imagined basically as writing 4 into 1 into 1 into 1, so on. So all the other into 1s can be mapped like this. 4 goes to alpha plus 1, and then if 1 goes to beta plus 1, this one goes to gamma plus 1, this one goes to delta plus 1. But when you solve, effectively beta turns out to be 0, gamma turns out to be 0, delta turns out to be 0, and so on. Only alpha plus 1 is 4, which means alpha turns out to be 3. So all the beta, gamma, everything is 0, 0, 0, which means you don't consider them because a prime to the power 0 is effectively 1, which means 1. So multiplying a number by 1 doesn't change. But over here, alpha equals to 3 is something we did derive. So this becomes case number 1. Solution alpha equals to 3 will work. What does that mean? That if I have a number n, which looks like a random prime, let's say p's cube, this number will have exactly 4 divisors. I hope this part should be clear. Let's take a quick example in this also. Let's say n was given as 3 cube. That is basically 27. Let's see the divisors of 27. 1, 3, 9, and 27. Voila, you have exactly 4 divisors? Yes, you do. Which means this idea is actually correct. So n, if looks like a prime's cube, will have 4 divisors. This is solution 1. Solution 2 according to me is same thing. If I write alpha plus 1, beta plus 1, and so on equals to 4. Now instead of plugging 4, I can divide 4 into 2 halves like 2 into 2. And then into 1 is still there, but it doesn't matter. And this time, this 2 gets mapped to alpha plus 1. And this 2 gets mapped to beta plus 1. Effectively giving me alpha plus 1 equals to 2, which means alpha becomes 1. And similarly, beta plus 1 equals to 2, which means beta becomes 1. This means all the numbers which are of the form some prime, let's say p, into some, let's say other than prime, let's call that q. So all the numbers which look like the product of 2 primes, they are also going to have exactly 4 divisors. Again, let's verify. Let's say that n looks like, let's take a prime, let's say 3. Let's take another prime, let's say 7. This is 21. Let's see. Break down 21 and tell me the divisors in this. 1, 3, 7, and 21. That's all. 4 divisors. So 3 was a prime, 7 was a prime, their product was a number 21, and it had exactly 4 divisors. And this is all. Pause the video. I don't think you will be able to come up with any more solutions to this equation. And that being said, we have from our first idea, using the number of divisors formula, which is very, very clear, we have now figured out that if we are trying to form the smallest positive integer and we have to satisfy condition number 1, that is it has exactly 4 divisors. It's changed, not at least 9 more, it's exactly 4 divisors. We need all the numbers that look how? They look either like p cube or they look like p into q, where p and q both are primes, both are greater than 0. This is a very important conclusion, and this makes sure that condition 1 is now done and dusted. If I talk about numbers that look like p cube or pq, then I know I am satisfying condition 1 because I will land up with 4 divisors. This means that now all I need to analyze is condition 2. If I pick up their divisors, they should have at least greater than equal to d difference for any 2 divisors that I pick up. So I can now solve for these 2 cases separately. Let us begin. So from here on, solving for condition 2. We know that case 1 tells us n looks like p cube. Let's first of all write the divisors of n if n looks like p cube. N will have 1 as a divisor, p, p square, and p cube. Pause the video. Tell me if I'm wrong. 1 will divide p cube, p will divide p cube, p square will divide p cube, and p part 3 of course divides p cube. So these are the divisors that n has, 4 divisors exactly. And I have listed them in increasing order. Now I'm saying p is greater than 0. Okay. Now I am looking to satisfy the condition that if I pick up any two divisors in this, their difference is greater than or equal to d. Now let me draw a little diagram over here. Let's say the difference between 1 and p is d1. Let's say the difference between p and p square is d2. Difference between p square and p cube is d3. And let's note these equations down. Let's say that I want to keep d1, d2, d3 positive. So I'll say p minus 1 because p is greater. So p minus 1 is d1. P square minus p is d2. And p cube minus p square is d3. Now here is a thought. If I am able to satisfy the condition of these three differences being greater than or equal to d, listen very carefully. If d1 is greater than or equal to d, if d2 is greater than or equal to d, and d3 is greater than or equal to 3, then tell me, don't you think any other two divisors that I pick up, they will create an absolute difference greater than or equal to d? They will. Why? Let's say that you pick up p and p cube now. Now you know that d2 is greater than or equal to d. You also know d3 is greater than or equal to d. And p and p cube have this larger line, this larger red line. Now if d2 and d3 both are greater than or equal to d, then this line is actually d2 plus d3. Now d2 is greater than or equal to d, d3 is greater than or equal to d, then don't you think d2 plus d3 will automatically be greater than or equal to 3? It will. That means only the consecutive differences are something I want to satisfy, not everything. If I satisfy the consecutive differences, I will actually satisfy all possibilities of differences. And this is why I only need to work with these three equations. This is idea as of now. Let's even make something better on this. Now let's analyze. I am looking to create something like this. p minus 1 is greater than or equal to d. This is capital D. Capital D that was given in the problem, by the way. Don't confuse. That is why initially in the problem I took this as capital D. Capital D is this d that is given in the input. This equation is p minus 1. I took p common. In p square minus p, I took p common. So p into p minus 1 greater than or equal to d. And over here, I'll take p square common. So this is p minus 1 again greater than or equal to d. Now you will say, sir, why did you do this? I did this to identify a very important thing. I right now had said that we are looking to satisfy three equations. But is that so? We are actually looking to satisfy only one equation. If p minus 1 is greater than or equal to d, then this portion will be greater than or equal to d. Automatically, this part into p, knowing that p is greater than 0, will go greater than or equal to d. Similarly, if p minus 1 is greater than or equal to d, then into p cube will automatically, into p square will automatically be greater than or equal to d. This means that if the first condition is true, automatically condition 2 and condition 3 are also true. This means that I started off by actually thinking I had to check so many equations, but I have landed up with only one equation. That is, if you are able to figure out a p value which is greater than or equal to d plus 1, I shifted 1 there. If you are able to take some prime p such that it is greater than or equal to d plus 1, then that prime p, or rather plug that p and p cube as a number n, is actually going to work. Let's see this with an example. If let's say I would have taken d equals to 2, okay, and I said you want a prime that is greater than or equal to d plus 1. So a prime that is greater than or equal to d plus 1 is actually 3. Let's take this. Let's talk about n now. N, or a rather, I would have taken n, a is the number that I want to print rather. A would be 3 cube, that is 27. Let's list the factors, 1, 3, 9 and 27. So of course it has 4 divisors. That means it has at least 4 divisors. So condition 1 is correct. And pick up any 2 divisors. Pick up 1 and 3. Pick up 3 and 27. Pick up 9 and 27. Pick up 3 and 9. Whatever you pick up, the difference is still greater than or equal to 2. So don't you think 27 is a right answer for this case? Now you might argue that d equals to 2. Actually the answer was 15 in the test cases. Why are you saying 27? I haven't still completed the problem. This is just the derivation I took from case number 1. We still have to go for case number 2 where the form is pq. Let's go to case 2. Okay. Now, if you have understood case One, pause the video and think it once more. And now I think case 2 is going to be a little similar. N now looks like PQ format. Let's first list the devices. Same thing we did in PQ. 1, P, Q, and PQ. Where P is greater than Q. Q is greater than 0. And just for generality purpose, let's say P is less than Q. P is the smaller prime. Now 1P, Q, and PQ, they are in increasing order now. Let's draw this diagram once more. D1 difference, D2 difference, D3 difference. What am I looking to satisfy? I'm looking to satisfy that P minus 1 is greater than equal to D. I'm looking to satisfy that Q minus P is greater than equal to D. I'm also looking to satisfy that I can say PQ minus Q, but if I take Q common, that is Q, P minus 1 is greater than equal to D. Now same question. We have 3 equations. We might think we want to satisfy everything, but from case 1 we just learned we did not satisfy everything. Only one equation worked. In this case, do you think we can still lower our searching thing that we want to do? Yes, we can. If we just satisfy condition number 1 and condition 2, then automatically everything is clear. Why? Because condition 3 is automatically handled if condition 1 is true. Condition 1 says that P minus 1 is greater than equal to D. If P minus 1 is greater than equal to D, then into Q will automatically be greater than equal to D because Q is greater than 0. That means if 1 is true, by subsequent 3 is also true. And the 2 is something that is not related anywhere else. So I need to check that also. So irrespective of case 1, case 2 tells me that over here you need a little extra. You need to also make sure P is greater than equal to D plus 1. And then you also need to make sure that Q is greater than D plus P. I hope this part should be clear. Let's run this once more on our case. Now I think it's going to look much clearer. When our case was D equals to 2, for now a case where number looks like PQ, let's figure out P once. P is the number that is just greater than equal to D plus 1. D plus 1 means 3 because D is 2, so 2 plus 1, 3. So P is a prime. 3 will fit because 3 is greater than equal to 3. So a prime greater than equal to 3. Okay. Now Q should be greater than equal to D plus P. That is 2 plus 3, that is 5. So greater than equal to 5, a prime. 5. You can take 5. 5 is greater than equal to 5. Let's see. Multiply gives you 15. That means N should be 15. Let's check. 15 has 1, 3, 5, and 15. Yes, 4 divisors. Pick up any 2 divisors. Is their difference greater than equal to 2? It is also right. That means 15 is also an answer. So now I actually solved sample case 2 for you. Sample case 2 was saying D was 2. I've proposed an answer that was either P cube 27 or an answer that was either 15. And then because we wanted even the smallest out of everything, we took the best case 15. So this is actually now your idea. You have 2 cases now. One is P cube format, one is PQ format. So you would now want to explore both ideas and take the best out of them. Whichever is the minimum gets you your correct idea. Similarly, now if I in the initial had told you that D equals to 3, answer according to me that A or N, whatever you call this, I'm actually confusing the variables every time, so don't worry. A, N, it's basically the same thing. A or N basically according to me was 55. Why did that come? Let's check both cases. If D is 3, then D plus 1 is 4. So let's figure out a P that is greater than equal to 4. 5. I think 5 is right. So let's figure out P cube, that is 125. This is A. This is one possible answer. Let's take the other route. D plus 1 is 4. So P according to me should be 5. Then D plus P in this case will become 3 plus 5, that is 8. So a prime that is just greater than equal to 8, which can be related with Q, is 11 now. So P into Q is actually 55. PQ will be known as 55 and this is A. So one answer is 125, one possible answer is 55. What is the best out of that? 55. Hence 55 is the answer. I think this checks out. I think this is the wow moment. Pause the video and think it once more, whatever idea that I told you as of now. Let's revise this quickly. Okay. I started off by saying I need to find the number of divisors. For that I said this is the formula. I solved it with 2 sort of equations. Once I plugged 4. Next time I plugged 2 into 2. I got 2 general formats of how the number A or N looks like. Either it's a primes cube or 2 primes product. Then I analyzed both cases to satisfy condition 2, that is divisors should have at least greater than equal to difference. I figured out that this is the equation that comes from case 1 and this is total 2 equations that come from case 2. If I now verified both cases and I get 2 possible A's or N's, the best A, the best N, whatever you call that, is taken. I cross verified that for D equals to 2 also. easily saw 15 and 27 both were answers, so we took 15 better. And for d equals 3, 125 and 55 both are actually correct answers, we took 55. And this is why this works. I hope this is clear. Now let's talk about implementing this logic. Okay, this is actually very, very fun part. I can actually argue that brute implementation works. What do you mean by brute? Basically, you're looking to find the first prime that is greater than or equal to d plus 1. Then the next best prime that is greater than or equal to d plus p. So if I write a very simple logic of a for loop that starts from d plus 1 and then goes on and on, let's call this an I iterator. And then inside this, I can call a very popular method called as sqrt method to check whether I is prime or not. And as soon as I find I to be prime, I can say that the value of p is I. Now this idea that I did, I can do the same thing on a different page, and I can say that I'll call this once more time, and then I'll first start with d plus p, move on and on. Again, this is the number I for I'm checking, and inside this again run the sqrt method. And as soon as I find that I is actually a prime by this primality testing, q becomes I. So this is the brute idea, and my argument is this works. Why? Because if you talk about the sqrt method, we all know that sqrt method actually runs in O of root of whatever number you pass inside this. Maximum in this case, we know that d is given in 10 raised to 4 order. So I would be talking about 10 raised to 4 order, O of 10 raised to 4 root as the square root method's complexity. But this for loop's complexity is something you need to know. This is actually a very important fact. This is something you can also remember for future problems. When do you think this loop actually breaks? This outer loop actually breaks as soon as you find the next prime from d plus 1, correct? Now this is actually a fact that if we generalize and say there is, let's say, an nth prime, from nth prime to the n plus 1th prime, the difference between these two numbers is approximately given as log base e. E is the natural log of n. And this is the fact. Now I can plug this fact back in this complexity calculation, and I can say that this loop is going to run roughly in O of log base e of 10 raised to 4 order. That is log base e of maximum d order. This means that now this will translate to roughly like O of 10. You can do this on calculator. This is like approximately O of 10, and this is going to be O of 10 raised to 2. This means that if I want to find p, I actually have a complexity of 10 into 10 raised to 2. That basically means 10 raised to 3 simply. And then if I want to find q, that is another 10 raised to 3 complexity, and voila, our brute solution actually works. We wanted for one test case our complexity to run in 10 raised to 4 order max, 3 into 10 raised to 4 order. But now we actually came up with a solution that is 10 raised to 3. That is little lesser than that. It definitely works. So yes, my brute idea is correct. And this is the beauty of this problem. Teaches one more fact to you that nth prime and n plus 1th prime have an approximate difference of log base e, natural log of n. Great. I hope this is clear. Now, on basis of this fact, I don't think we need any more discussion on the pseudocode. We can directly jump to our main code and just look this in picture. What I have done over here is I have taken the test case variable, then I have taken d, then I want to find the next prime by passing d plus 1, that will be p. And when I pass p plus d, that will be q. And when I get p and q, then I know one possibility is p cube. So 1 LL, this is long conversion into p into p into p. And then the other possibility is p into q. And I compare both of them, that becomes my answer A, and I print it. And what is the next prime function? It is basically a very simple brute logic. I just barely pass n in this, and then I run sort of a for loop starting with n, that is the number I have passed. There is no upper limit to this because I know it's going to break roughly in log power only. And then I have this square root method testing, is prime variable. This is how a square root method looks like, starts with 2, j into j is less than or equal to I, j plus plus. If j divides I, then it's not a prime, and I break. If is prime is still true, then I know I want to return I because it is a prime. This is the square root method. So this complexity is going to be log base e of 10 raised to 4, you can say, which is approximately writing O of 10. Okay, this is something I did by Google, so you can also search this on your own. And the square root method is, you can say, O of 100 or 10 raised to 2 because it is square root of 10 raised to 4. So that is 10 raised to 2. This means this overall is 1000. Okay, this is overall 1000. That means this is 1000, O of 1000, and similarly this is also 1000. And then after that, this is pretty much constant. So this means for one test case, I actually have come up with a time complexity as O of 10 raised to 3. And what about space complexity? Basically constant, because I'm not using any extra space to get my answers. Everything is just simple variables. All right. So this is the beauty of the problem. It has taught you one more fact of the Divisors formula also. So if everything is a little bit confusing, pause the video, just reiterate once more and come back over here. I think it should be more clear. And that is all that is there in this problem. I hope you like the video. Thank you for watching.